Okay, visible, right?
Yes, ma'am.
Okay, so we did this in the last class. So what did we do? We calculated the RC delay for a very simple RC network that's only with one resistance and one capacitance. And then we found out the V out of T, that is the transient response, is equal to VDD into 1 minus e power minus T by RC. Then I actually gave a definition for the propagation delay, right? We want to see what time it takes for the output to raise to VDD by 2 from the time the input raises to VDD by 2. So for an output VDD by 2, we calculated TPD. This was LAN 2 RC. So that's 0.693 RC. So from now on, even though this is there, we conveniently ignore this and represent it RC. But the more accurate one is always LAN 2 times RC. Right? And after this, we defined unit NMOS. So basically, whenever we use NMOS as a switch, we know that it's operating in linear region. So from the current equation of linear region, we come up with an expression for the resistance of that switch, which depends on mu n COX, W by L, and the overdrive voltage. But although we know that the resistance varies with overdrive voltage, what we do, we consider the effective resistance R, which is the average resistance of the MOSFET when it is behaving like a switch, because we do not want to calculate the resistance for each overdrive voltage every time. Okay. So in other words, we can say R is proportional to 1 by mu times W for a minimum W by L. This effective resistance is for the minimum allowed W by L, minimum allowed aspect ratio. We know that R is inversely proportional to mu n and W. Similarly, we have diffusion capacitors at drain, gate, and source, right? So we do not want to calculate each and every capacitance. So we conveniently represent it as some effective capacitance C, where C here is nothing but all the capacitors at the gate, all the capacitors at the source, and all the capacitors at the drain. Though the capacitors at drain, source, and gate are not equal, they are comparable. So all these lie either in femtofarad or attofarad, depending upon the technology that we use. So for the ease of calculations, we consider they are equal and represent them using C, right? And yeah, so this, when you scale the width of the NMOS by a factor K, so that is when you increase the width of an NMOS by the factor K, then what happens to the resistance? Resistance gets scaled down by K, whereas the capacitors gets scaled up by K. So this is the RC representation not of a unit NMOS, but for an NMOS with width equal to K. Okay. So next we studied unit PMOS. Unit PMOS. So in case of a unit PMOS, we know that mu n is not equal to mu p. Mu p can be equal to half mu n, 1 by 3rd mu n, 1 by 4th mu n, because mobility depends on various factors. So for the analysis purpose, we just fixed mu p is equal to half mu n and went ahead with the analysis. So therefore, now since mu p is half mu n, I can represent the effective resistance of the unit PMOS as 2 times R. And that since the capacitance of this is directly proportional to the width, so capacitance can be represented as C itself. So even here, if you scale PMOS by K times, so then the resistance of the PMOS gets scaled down by K, that is it becomes 2R by K, and the capacitance gets scaled up by K. Next we come to an unit inverter. So we design a unit inverter in such a way that the effective resistance of the NMOS is equal to the effective resistance of the PMOS. so that the rise and the fall times are equal. See, here we cannot match the capacitor. See, if you try to make the effective resistance of NMOS equal to that of PMOS, obviously the capacitors of NMOS and PMOS differ, right? But these are parasitics. The delay is dominated by the load capacitance, which is much, much higher than the parasitic capacitors. So that's why we try to make the effective resistances equal so that the delays are more or less the same, right? So then we drew a unit inverter. For a unit inverter, in order to get the effective resistance of NMOS equal to that of a PMOS, we make the width of PMOS equal to 2, and therefore the capacitances will be equal to 2C for the PMOS, right? And here we drew the RC model for a unit inverter, and then we tried to calculate the propagation delay. So the propagation delay of this inverter is 3 times RC, right? If you cascade the output of an inverter with another unit inverter, then the gate capacitances of the second inverter also contributes to the charging and discharging of the capacitances at this point. I mean, basically, these capacitors at the gate contributes to the switching speed at this point. So therefore, with an inverter cascaded, we calculate the propagation delay, and we saw that with another inverter cascaded, the rise and the fall times, that is the propagation delay, is equal to 6 times RC. What else did we do? Yeah. So then we did some sizing of the transistors for various complex gates or universal gates only we did, right? So now, assuming that the unit inverter has WP by WN is equal to 2 by 1, we try to size the transistors of a NAND gate so that the effective resistance of each branch that we see here is equal to R, right? So first we did on the NMOS side. On the NMOS side, for the effective resistance of this to be equal to R, we want the effective resistance of this transistor B as well as this transistor A to be equal to R by 2 and R by 2, so that the effective resistance when it is in series is equal to R, right? So therefore, we make the width of both these transistors equal to 2. Okay. So now we come to the PMOS side. So the PMOS side has 2 branches, right? So the worst case charging will be when only one of these PMOSs is on. Therefore, we try to make the resistance, effective resistance of each branch equal to R. For the effective resistance of each branch to be equal to R, we need to size these to be equal to 2 and 2, so that the resistance of each branch is equal to R. This is for the worst case raising delay, right? The best case will be when both of these are on. There are 2 resistors connected in parallel and the resistance will be R by 2. That will be the best case, right? For the worst case, only one of these 2 transistors is on. So that's how we went about sizing the transistors in 2 input NAND gate. Next, we came to the NOR gate. Right. Again, we took a unit inverter as the base. Based on that, we tried to size the MOSFETs, NMOSs and PMOSs so that the resistance in each branch is equal to R. So here you see that the PMOS has only one branch. The worst case raising time here will be when both of these transistors are on. So we want the effective resistance of this branch to be equal to R. So therefore, we need each of the transistors to exhibit a resistance R by 2 and R by 2. We sized the transistors PMOS so that each of them exhibits a resistance of R by 2. Therefore, W of both of them are 4 and 4. Right? So similarly, on the NMOS side, the worst case fault type should encounter an effective resistance R. So therefore, each of them will have a width equal to that of a unit NMOS. So everything with respect to the unit inverter whose aspect ratio is 2:1. So PMOS is 2 and NMOS is 1. This is all we did in the last class. Okay, so now let's continue with the class. Let me stop sharing this. Okay, so now can you all size the transistors of a 2-input NAND gate if my unit inverter has a ratio 3:1? PMOS to NMOS width is 3:1. Then how will you size the transistors of a 2-input NAND gate? My unit inverter has the width of PMOS equal to 3 and width of NMOS equal to 1. Then I want you to size the transistors of NAND gate.
PMOS 3, NMOS 2, ma'am.
Sorry?
PMOS 3 and NMOS 2.
Okay. So PMOS will be 3, 3, 2, 2. Correct?
Yes, ma'am.
No doubts in this. No, it is clear. I mean, it's not very difficult. Okay, so now suppose I have WP by WN as 4:1. Then,
4 and 2.
okay, so PMOS transistor size will be 4, while the NMOS transistor size will be 2. Right? Okay, now can you size 2-input NOR gate? 2-input NOR gate when WP by WN is 3:1.
PMOS will be 6 and NMOS will be 1, ma'am.
Okay. Is that right? If WP to WN of an unit inverter is 3:1, then here you will have PMOS is equal to 6, so that both of them will give an effective resistance of R by 2 and R by 2, and NMOS will be 1 and 1. No doubts in this, right? I assume this is clear. So basically everything is with respect to unit inverter. Based on WP and WN of unit inverter, we need to do the sizing. Now, okay, I'm not going to draw, but can you tell me for a 3-input NAND gate, 3-input NAND gate, 3-input NAND gate, if WP is to WN is equal to 2:1, right? So then what will be WP NAND and WN NAND for a 3-input NAND gate? Okay, if it is 2:1, if the unit inverter is 2:1, tell me what will be WP NAND and WN NAND.
WN is 3.
Okay, this is 3.
WP is 2.
Is this right? Okay, now for the same ratio, tell me WP NOR WN NOR 3 inputs. WP NOR WN NOR 3 input.
6 and 1.
Is that right? 6 and 1. I'll give you some time. The rest of you, please go through this, sit and analyze. If you need some time, let me know. So we are sizing it in such a way that the effective, worst case, the effective resistance is equal to R. Is this clear to all of you? Please reply, is this clear?
Yes, ma'am.
Yes, ma'am.
Okay. So, okay, we'll do two more, okay? So again, 3 input NAND. For a unit inverter, WP is to WN equal to 3 is to 1. You have to tell me WP NAND and WP NOR. Sorry, WN NAND.
It's 3, ma'am. Both will be 3, ma'am.
Both are 3. Okay, so both of them are 3 and 3, right? Can you tell me what's WP NOR now for 3 input and WN NOR? Three input
9
NOR
and 1.
gate with a unit transistor ratio 3 is to 1. Unit inverter ratio 3 is to 1.
9 and 1.
What is 9 and what is 1?
PMOS is 9 and NMOS is 1.
Okay.
Yes, ma'am.
So based on the mobility, you derive the width of the PMOS and NMOS, and then you size the other gates in such a way that each branch will have an effective resistance R. So now, let's take mu p is equal to half mu n. Now let's fix it. Since now you know how to size based on mu p and mu n, let's fix it to be equal to half from now on for all problems. Okay. So now, can you size the transistors for the schematic? Draw the schematic of NMOS, draw the schematic of PMOS, and then size the transistors for this schematic. Okay, is this right? Schematic, I assume you already know how to draw the schematic. We have done it previously. Is this right? Any doubts?
Ma'am, PMOS will be 4.
Okay, first tell me NMOS. Tell me the width of A and B.
A and B 2, ma'am.
So A will be 2, B will be
B
2.
will be, C will be 1, ma'am.
Correct, C is 1.
And 4,
PMOS
4, ma'am.
4 here,
4,
4,
again 4, ma'am.
4. Very good. Right. So here you have 2 branches in NMOS and 2 branches in PMOS. So when A and B are 1 and 1, this branch will be conducting. So you have to size the transistors A and B in such a way that it will give an effective resistance of R. So effective resistance of A NMOS will be R by 2, B NMOS will be R by 2. So therefore we size that as 2 and 2. Another branch consists of only one transistor, which is similar to that of an unit NMOS, right? Therefore the size of it is 1. Now again in PMOS, we have 2 branches. One is A and C, the other one is C and B, right? So now we have to size the transistors A and C such that each of them offer a resistance R by 2. Since a width of 2 in PMOS offers a resistance R, a width of 4 in PMOS offers a resistance R by 2, and therefore both the branches should be sized as 4 and 4. Any doubts in this? Okay, so now, can you do this? Draw the circuit and then size the transistors. Gautam, are you there? Gautam TK, are you there?
Yes, ma'am.
Okay, can you tell me what are the sizes of A, B, and C of the NMOS?
It will be 2, I think.
2. What about this?
Same, 2.
2. This?
C is also 2.
Yeah, good. So now again you have two branches here. One is A and C. So the effective resistance of A and C should be R. So therefore A should have a resistance R by 2 and C also should have a resistance R by 2. Therefore the width of it is 2, 2. Similarly B and C. Right? Now what about here PMOS, Gautam? You have this branch wherein the effective resistance should be R. So each of it should have R by 2 and R by 2, right? So therefore, what are the resistances here? I mean, what are the widths here?
C is 4.
C is 4. C is this. C is a standalone, not a standalone. There is only one transistor in this branch, no? So this is almost equivalent to that of a PMOS inverter, a PMOS in a unit inverter. Correct, Gautam. Gautam, are you there?
Yes, ma'am, I'm thinking.
Yeah, you think. So now you have two transistors A and B in PMOS. So if you have their widths equal to 2, then it will provide you with an effective resistance R. But we want the effective resistances series combination of both A and B to be R. So each one of it should have a resistance R by 2 and R by 2. Correct? So now what should be the width of A and B such that their resistances are R by 2? This branch looks similar to that of a NOR gate, 2-input NOR gate, right? Two transistors PMOS in series.
And 4.
Correct. So it should be 4 and 4, right? Because a width of 2 gives you a resistance R, a width of 4 gives you a resistance R by 2. Right? So therefore, width of 4 gives a resistance of R by 2 for A, R by 2 for B. So when this path is conducting, then the effective resistance is R. Okay, Giri Prasad, what about C?
C.
What should be the size of C here? PMOS.
2.
2. Good. So since this has only one PMOS in this path, the effective resistance of this should be equal to R. Therefore, we size it similar to that of a unit inverter whose width is 2. Clear. Okay, thank you. Y is equal to A plus B into C plus D. Bar. Okay, let me draw the NMOS side. I want all of you also to draw along with me. Okay, is this right? So yeah, this is the output Y. Dinesh, are you there?
Yes, ma'am.
Yeah, can you tell me the sizing of this
Ma'am,
on the
for NMOS,
on the NMOS?
ma'am,
Yes.
for D is 1,
Okay, D is 1,
C is 2,
C is 2.
and in here,
What about A and B?
and
So
2,
this,
2.
yeah, right. 2 and 2. Yeah, thanks. You can mute yourself. See, A and C is in one branch, right? For the discharging. So therefore, the effective resistance, that is the series combination of these two, should be equal to R. Therefore, each of them will have a resistance, should have a resistance R by 2 and R by 2. Therefore, we size the transistors A and C as 2. Since C is already 2, B also should have a resistance R by 2. Therefore, B is also 2, so that this effective resistance is R. As you can see in the NMOS path, D is the only resistance between Y and ground, similar to that of a unit inverter. Therefore, the size of it is 1. Is that okay? Now, Geetanjali, are you there? Tabassum, are you there?
Yes, ma'am.
Yeah, can you tell me the sizing for the PMOS?
Ma'am, A, B, and D, if you consider, it will be 6, 6, and 6.
Okay, so this is 6, 6, and 6. Correct. So R by 3, R by 3, and R by 3. What about this? C. If this is R by 3, then what should be the resistance of that? This is the branch, right, for charging. Correct? So now,
Yes.
yeah, what should be the resistance of this? So that this resistance is R.
6 only.
How 6? So if it is 6, this will be R by 3. This is also R by 3. Therefore, the effective resistance of this is 2R by 3. No, it's not R. Correct? What resistance should you connect in series with R by 3 so that you make the effective resistance equal to R?
2R by 3.
Correct. So you have to connect a resistance of 2R by 3 so that the effective resistance is R. So for a resistance of 2R by 3, what should be the width of C? For R by 3, it is 6. For 2R by 3, what should be the width?
3.
Correct. Right? So now this branch also has an effective resistance R, and this branch also has an effective resistance R. So here you have R by 3, R by 3, and R by 3 in parallel, which will give you an effective in series, which will give you an effective resistance R. Here you have R by 3 and 2R by 3 in series, which will give you an effective resistance R. But there is another sizing that you can do for this as well.
Mom, can we do 8844?
Yeah, exactly. That is also correct. That is also correct. Now, if you consider this branch first, you will basically size this as 4 and 4, right? So that the resistance offered by this is R by 2 and the resistance offered by this is R by 2. So that the effective resistance is R by 2 in series, effective resistance is R. So now this is R by 2. When I come to this branch, I want the series combination of A and B also to be R by 2 so that D in series with A and B is R. So if I want this series combination to be R by 2, then I can size the transistor so that A gives a resistance R by 4 and B also gives a resistance R by 4. Correct? And the effective width corresponding to that is 8 and 8. Now if you see, D gives a resistance R by 2, A gives a resistance R by 4, B gives a resistance R by 4, and the series combination is R. On the other branch, D gives a resistance R by 2, C gives a resistance R by 2, and the series combination is R. So both these sizings are correct. You can either size this as 6, 6 and 6, 3 here, or 4, 4, 8 and 8. Both these are correct.
Ma'am, but it should be 8844 only, no, ma'am.
Why?
How we can scale like 6, ma'am?
Why not?
Because it's R by 2 only, no, ma'am. Upper side, ma'am. D, it's R by 2.
Which is R by 2? D, if you
D,
do
ma'am.
it,
D.
if you do this as 6, it is not R by 2, right, Mohan? It's R by 3. It's R by 3. You make this resistance equal to 2R by 3. So that the effective resistance is R. You get that?
Ma'am, 1 second, ma'am, please.
Yes, yes. Okay, I'll give you some time. Please think about it and let me know if you have any doubts. But when you
Sure,
have to do
sure.
a layout for this, it's always good if you have these sizes in multiples of 2 because it's easier to fit it in a layout.
So if we consider any PCB, so all the transistors will be of different widths, is it? Like many
Oh,
will be.
definitely.
So like they will be specifying the width of each transistor, like even if there are millions of them, is it like?
Oh, yes. Yes, basically, yes. So what you do is, see, generally for these type of structures, it's very rare that we do a manual layout. Okay, because here it is behaving like a switch. This is a digital circuit, right? There are many tools wherein you just write the code. This you can anyway write in HDL, right? You can write a code in Verilog, right, Kirtana? You can just say y is equal to a plus b into c plus d the whole bar. You can
Yes.
write a code in Verilog and you can get the output. From the Verilog code, in order to generate layout, there are many tools. Okay, you just give Verilog code as input. That tool itself will do the placing, the tool itself will do the routing, and tool itself will give you a layout which you can send it to fab directly for fabrication. So, but in some very rare cases like ASIC, application specific, where you want, I want area to be minimum, I want power to be minimum. So there are very rare cases wherein actually manual layout design is required, which is for ASIC, application specific. But for any general layout, tool itself we do it. Even in our college also we have a tool in Cadence. Okay, so there's a tool called Genus in Cadence for synthesis from Verilog code in order to create a netlist. Okay, if you just give Verilog code as the input to Genus, it will create, and you have to give all the constraint like my clock is this much, I have this many inputs, I have this many output, everything, all these details. If you give, it will give you a synthesized netlist. The name of the tool is called Genus. Okay, you can try this. It's very interesting. Name of the tool is Genus, and this is from Cadence. This is from Cadence. Now, so for Genus, what you do, you give just the Verilog code. Verilog code with your clock speed. Yeah, there are certain things that you should give as input. Your clock speed, rise time, fall time, to be more accurate. Okay, you have to give, if you give all this as input, it will directly give you a netlist, pin netlist generated. Okay, so this netlist, if you give as input, this netlist, if you give as an input to Innova's tool, this is also by Cadence. I think it's, I don't know if it's VUS or VAS. Okay, so this netlist, if you give it to the input Innova's, then you will directly get a GDS file, which is nothing but the layout of the Verilog code. So there are tools to do this, but of course manually also you should know how to do for application specific requirements. That's why we are learning all this.
Yes, ma'am.
Okay, Mohan, do you analyze? Do you still have doubts?
Yes, ma'am, I got it, ma'am.
You got it. Anybody has
Yes, ma'am.
doubts in sizing? Should we do more problems, or I'll give you some problems as homework? You can try this because, let's move on. So you can try this AB plus C plus D bar. Okay. One more will be, let me give you an extension of this. Okay, these two I think you can just take down and then try this. Okay. So I hope all of you are clear with how you have to size the transistors based on the sizing of a unit inverter. Okay. So also I think you should, when you come back to college, you should try these tools. It is quite interesting. If you're interested in digital VLSI, you should definitely know at least one tool wherein you can generate netlist from Verilog code and then layout. It's good to know. There are many, right? You have one from Synopsys. There are many. Okay, so now let's move on. Okay, so sizing, I assume everyone is clear. So now what do? We'll try to calculate the delay. Now that we know the sizing, now let's try to calculate the delay for a 2-input NAND gate, okay? Okay, so this is a 2-input NAND gate, right? So this is A, this is B, this is A, this is B, so this is 2, this is 2. Here also it is 2 and 2, right? So let's also write the capacitors here. Since this is 2 at the input of the gate, you will have 2C. In fact, you should write the combination of both. So here you will have 2C. Here also due to PMOS, you will have, what's the capacitance here? Gate capacitance of PMOS. Joel, can you tell me what's the gate capacitance here? Gate capacitance, all capacitance is directly proportional to the size of the transistor, right? The width of the transistor basically. So can you tell me what's the size of this, Joel?
Yes, ma'am.
Yeah, how much is it?
Ma'am, is it 2C?
Yeah, this is 2C. So basically this input A goes to both PMOS and NMOS. Therefore, the total capacitance at A gate is how much? Correct? 2C in parallel with 2C. Therefore, you will have 4C at the gate. Is that right?
Yes, ma'am.
Yes. So similarly, can you tell me what is the total capacitance at the gate B? See, the NMOS at the gate of A has a capacitor 2C, right? Because its width is 2. PMOS width is also 2. Therefore, it will have a capacitance of 2C at the gate. So now this input A goes to both PMOS and NMOS. Therefore, the total capacitance is 2C plus 2C, which is 4C at A. Right, Carmugilan? Now,
Yes,
can
ma'am.
you tell me at B, what is the total capacitance?
4C, ma'am.
Correct, it's 4C itself because the sizes of B are also 2 and 2. Therefore, at the gate, you will have total capacitance equal to 4C. But then this doesn't contribute to charging and discharging at the output. But we'll see what it contributes to a little later. Okay, I'll just remove this. Now, let's concentrate on what actually is contributing to the charging and discharging at the output. Okay, so here you have, so here you have A and here you have A. Okay, so now here, this is the, okay, this is the source, this is the source, this is the source, and this is the source, right? So now you have a capacitor, source capacitor here, which is equal to 2C, correct? Because its width is 2, we just approximate all the capacitances, that is the capacitors at gate, drain and source as 2 and 2, right? So what do you think is the capacitor here? Kartikeya, can you tell me?
2C, ma'am.
2C, correct. But do you think this will contribute to charging or discharging?
No, ma'am.
No. So yeah, we ignore that. And here we have a capacitor 2C at the drain of A and another capacitor 2C at the source of B, right? So we have 2 at this point. The source of B is connected to drain of A. So we have a capacitor 2C at the source of B and at the drain of A. Do you understand this? Why I wrote 2C here? Why I wrote 2 capacitors in parallel at this point? You have one capacitance at the drain of A and one more at the source of B. The 2 are connected here, right? So since the width of A and B are 2, you have one capacitance 2C due to the width of A at the drain of A, and one capacitance 2C at the source of B. Because the width of B is also 2, it will be 2C and 2C. One is due to the drain at A drain, and the other one is due to B source. Did you get that?
Yes, ma'am.
Okay, now Krishna.
Yes, ma'am.
Now, can you tell me what are all the capacitances at this point? This is the output Y. This is the point at which I take the output Y. What are all the capacitances at this point?
One will be a drain of B, that's 2C.
Yes, 2C due to the drain of B. Then?
And then due to A and B source, 2C will come again. So
No,
we'll
no,
have
it
2
can
again.
be drain only. Drain
Ma'am,
only, right?
due to A and B also, we'll have 2C.
Yes, you will have 2C. Drain of A and B. See, drain are connected at the output.
Okay, yeah.
Okay, 2C, and then 2C again, right? So one is
Yes,
due
ma'am.
to the drain of B, NMOS. The other is due to the drain of A, PMOS. The other is due to the drain of B, PMOS. Correct? Okay. So next again you will have 2C and 2C here at the source of PMOS. But do you think that will actually be a part of charging and discharging?
No, ma'am.
No. So therefore, we can conveniently ignore that 2C and 2C. Right? Is that clear how I wrote the capacitances here? Any doubt in this? So now in the next one, I just put all the capacitances together. Okay. And then represent it using a single capacitor. Have A, have B here, then B and A, right? So here you have 4C, right? 2C and 2C in parallel, and here you have 6C, correct? It's 2, 2, 2 and 2. Okay, so now if I have to represent the discharge, the discharging happens when both A and B are equal to logic 1. Then I'll have a path which is something like this. I'll have a resistance R by 2. I'll have a resistance R by 2 going to ground, right? R by 2 here. So I'll have 4C here. And then I'll have a 6C here, right? So here the worst case discharge when this 4C is also charged and this 6C is also charged, and both of them have to discharge to ground, right? That is the worst case during the discharge time when both A and B are 1. And as you can see here, this is the output. This is the output Y, right? So as you can see here, you have two RC ladders, right? Which is something similar to this. So you have a ground here, then you have R by 2 here, and then you have 4C going to ground. And then you again have an R by 2 here, and then you have a 6C going to ground. And this is the output Y, and this is ground because we are considering discharging, right? So this is ground. So this will be R by 2, and this will be R by 2. As you can see here, calculating the impedance of this network is not easy, right? Because you have two RC loops. It was not as simple as an inverter where you had only one R and one C. You have an RC ladder here. Do you recognize that? You have an RC ladder. Therefore, in order to calculate V out of S, which is this, and if you consider this as an input, right? If you want to calculate V out of S by V in of S, then you will have to apply two KVL loops and then solve in order to get one complicated expression. Do you get this?
Ma'am,
Yes.
ma'am, the capacitances on the PMOS side, they have to be connected to VDD, right?
Here, this, right?
The ones in the drain side, like, is
Yeah,
it
the
to the
ones on
VDD
the
or
drain
from?
side are connected to VDD. But last class I told you, when we are calculating the effective capacitance, when we calculate at any node, so VDD does not contribute, it does not change the delay time. Therefore, when we are calculating the effective capacitance, we directly take that as ground, similar to a small signal analysis. So whatever is
Okay.
connected to a DC source, we take that as ground. So that's why we have 6E here. Yeah, you're right. This is actually connected to VDD, but as far as delay is concerned, this is connected to AC ground because it's not changing. That does not contribute to the change in delay.
Yes.
Okay. Okay, so this is clear, right? So basically what I'm trying to tell you is for a 2-input NAND gate, if I have to calculate RC delay, then I get two such networks. You'll have to apply KVL to both the loops, solve, and then get V out of S by V in of S. Then again take the inverse Laplace of this in order to get the time delay. So for 2 itself, it is difficult. But if you have a 3-input NAND gate, N-input NAND gate, it is more difficult, right? So therefore, we go for another type of model for delay calculation, which is called as Elmore delay. Because using RC delay, oops. Okay, using RC delay, it becomes very cumbersome for calculating delays for larger circuits, right? So therefore, we'll go for Elmore delay. Okay, so we'll just work out a simple example as to how we calculate the Elmore delay. So we don't derive this, how we calculate it, but then we should know how to use this to calculate the delay of other circuits. Okay, so I'll just take a small example and then we'll work it out. Okay, so this can be used whenever you have an RC network with no loops. Okay, so this can be used whenever you have an RC network with no loops. And then, okay, let me draw one. Suppose you have R. This is a very generic model, okay, not related to any of the gates. This is a very generic model. So whenever you have some circuit which looks like this, V0, here is Vin. Let's call this R1, R2, R3, R4, C1, C2, C3, C4. Okay. So whenever we have a circuit that looks like this, that is whenever an RC circuit has no loops, the root of the tree is the voltage source. So this is an RC tree, right? So the root of the tree is the voltage source. This is the voltage source. And the leaves are the capacitors. Okay. So the leaves are the capacitors. So Elmore delay can be calculated as follows. Okay. So we say TPD, T propagation delay, using an Elmore delay is, if you have I branches, then it is RIS into CI, sigma RIS into CI. So we'll calculate the delay of this so that this, whatever I've written here, becomes more clear. Okay. What it means, I'll tell you. When I say RIS, it means the resistance that is shared from the input to the output path. Okay. And Ci is all the leaf capacitors. So I'll explain what I mean by RIS. Now let's calculate the delay at various points. Okay, let me call this as V01. Let me call this as V02. Let me call this as V03. And let me call this as V04. Okay. First, in order to calculate V04, let's calculate the delay from the input to the output of V04. Let me write that as TPD4. So here you see that all these resistors come in the path between V in and V output. Right? If I have to calculate TPD at V04, here you see that all the resistors here come in the path from Vn to V04. So therefore, I can write the delay as, this is an approximate delay, I can write the delay as R1 into C1, okay, R1 into C1 plus the shared resistance for C2 is R1 plus R2. Okay, the shared resistance for C2 is R1 plus R2 into C2 plus the shared resistance for C3 is R1 plus R2 plus R3 into C3 plus shared resistance for C4 is R1 plus R2 plus R3 plus R4 into C4. So this will give the approximate delay when, and we use this when we have more RC branches, because applying RC delay model to this is very, very cumbersome. Therefore, we use Elmore delay model. So is this clear now? How to calculate the propagation delay of TPD4? So now here we see that all the resistors are in the shared path. So while calculating the delay due to the capacitor C1, we just take the resistor R1. So first term is R1 into C1. So when we are calculating the delay due to the capacitor C2, we see that both R1 and the resistance R2 are in its path. So therefore, we write R1 plus R2 into C2. Calculating the delay due to C3, we see that R1, R2, R3 is in the path. So therefore, R1 plus R2 plus R3 into C3 plus the last term will be R1 plus R2 plus R3 plus R4 into C4. So this is the propagation delay for this network. Now, let us calculate the propagation delay at V03. Let's calculate the propagation delay at V03. Okay. So V03 is here. V03 is here. So there is no change in the first few terms. Okay. So now R1 is in the shared path. It is in the path from Vn to V03. Therefore, we'll have R1 C1. Due to the capacitor C2, R1 and R2 are in the shared path. That is, it is in the path from Vn to V03. Therefore, we'll have R1 plus R2 into C2 plus for C3, R1, R2, R3 is in the path from Vn to V03. Therefore, we'll have R1 plus R2 plus R3 into C3 plus, now there's a difference, right? So we'll have to calculate the delay term due to the capacitance C4, but we see that R4 is not in the path from V into V0 3, right? So therefore the resistance here will be just R1 plus R2 plus R3, because these are the only resistors in the path from V into V0 3. But still, there is this term due to C4 term must be included, because there might be C4 discharging through this path or charging through this path. So therefore, the term due to all the capacitors must be included, because each of these capacitor might have been charged and should be discharged, or it might be discharged, you should be charging the capacitors. Therefore, all capacitors, the terms due to all the capacitors must be included in the Elmore delay propagation, Elmore propagation delay. But you should be able to choose what resistors you should include in TPD while calculating the delay. So you should only include those resistors that are in the path from input to output and are shared. Now, I want you to calculate TPD2 and TPD1 so that you become more clear. I want you to calculate TPD1 and TPD2 so that you are more clear. So you should have a term with respect to all capacitors in the circuit, but you should cleverly choose the resistors only in the path from V into V out. That's the trick. That's it. Nothing else. Is that clear? Now I want you to write what's TPD2 and TPD1. Once you do this, I'll just summarize what we did today and we'll wind up. Laksh, can you tell me what's TPD2?
Yes, ma'am. TPD2 will
Let me write. Okay. So, TPD2 is equal to what?
R1C1
R1C1, correct?
plus R1 plus R2 into C2
R1 plus R2 into C2,
plus R1 plus R2 into C3
correct? Plus R1 plus R2 into C3,
plus R1 plus R2 into C4.
very good. Correct. Thank you. So this is TPD2. Right? This is how you calculate Elmore delay. Who will tell me what's TPD1? Manikandan, can you tell me?
Yes, ma'am. R1 times C1 plus C2 plus C3 plus C4.
Correct. That's it. That's it. You're right. So is this clear now?
Yes, ma'am.
Yeah, I hope this is clear. Right? So we'll just summarize what we did so far and then we'll wind up. So what did we do? Okay. So we started off the class with a unit inverter whose WP is 3, Wn is 1, which means mu P is equal to 1/3 mu N, right? Mu P is equal to 1/3 mu N. So we started off this unit inverter and we tried to size the transistors in NAND and NOR gates. So based on this, in order to achieve an effective resistance R in this path, this resistance should be R by 2 and R by 2, and therefore you size these two as 2 and 2, right? Now, effective resistance of these two should be R and R. Therefore, you size them as 3 and 3 because the unit inverter width itself I've given as 3. Next, similarly, since the unit inverter PMOS width is 3, in order to get a resistance R by 2 and R by 2 here so that the effective resistance is R, you size them as 6 and 6. And the worst case fault time here is when one of these two transistors is on. Therefore, in order to get a resistance R, you size them 1 and 1. Similarly, we did it for a 3-input NAND gate, 3-input NOR gate, right? For mu p is equal to half mu n and mu p is equal to 1/3 mu n. Next, what we did is to size some of the complex circuits, right? Some of the complex circuits, like, I mean, you cannot exactly call this complex though. So AB plus C the whole bar, right? So what is this basically? Have we studied this earlier? What do you call this? You have an AND operation, you have an OR operation, you have an invert operation. So you call this as,
And or inverter.
yes, AND or invert to 1 based on the inputs here, right? So similarly, we try to size these based on a unit inverter. Mu p is equal to half mu n, again, so that all the effective resistances, the worst case charge and the discharge times are encounters an effective resistance of R. So we did another expression, and then we saw we can size these transistors in two ways, so that still we get an effective resistance of R during the charge and the discharge times, right? And then I gave you homework, as in you try to draw the CMOS circuit for this, schematic for this, and then size the transistor so that you have a effective resistance of R. Why are we doing an effective resistance of R, and why we are not meddling with the capacitors much here is mainly the delay capacitance at the output that dominates the delay is the load capacitance, which is much higher than the parasitic capacitance. So therefore, we are trying to make the effective resistances equal so that, you know, this R and C, charge and discharge, are equal. Okay. So now, next thing that we did was we tried to calculate the delay of a 2-input NAND gate using the RC delay model. Therefore, based on the width, we wrote the effective capacitances at each of these nodes, right? And then we simplified the circuit here. We saw that there are two RC branches. So if we have to calculate RC delay using this, then we'll end up with some complex expression, and therefore taking inverse Laplace transform in order to get the transient response and all is very cumbersome, and therefore we do not want to go with this type of a delay for very complex, not very complex, for complex circuits. It holds good only for inverters but not the other circuits, right? So therefore we are about to study another delay model, which is called as the Elmore delay model. So using this, we calculate the propagation delay. Okay, so the formula to calculate the propagation delay here is RIS into CI, which means here all the capacitors in the circuit contribute to the delay, but as far as the resistors are concerned, only the resistors that come in the path of input to the output contribute to the delay. So this is, as you can see, this is not as accurate as RC. It's an approximate delay model, but it's easy. The calculations are easy. That's the advantage. So for this example, we saw what is TPD at nodes 4, 3, 2, and 1. So now that you are comfortable in calculating the Elmore delay for RC networks, next class we'll try to find out what is the worst case rise time delay for 2-input NAND, 2-input NOR, 3-input NAND, 3-input NOR, and then we'll also try to find out propagation delay as well as the contamination delay. Okay, another term that I am introducing in the next class is the contamination delay. We'll see this for all the basic circuits. Once we do it for basic, I am sure you should be able to do it for any circuit. We'll do that in the next class. So that's it for this class. If you have any doubts, you can ask me or you can leave the class.